At the September 2016 International Astronautical Congress in Mexico, Elon Musk, the founder and chief executive officer of SpaceX, was presenting his ambitious plans to make the human species a multiplanetary species. And with a total focus on the colonization of Mars, this was the beginning of a gigantic and ambitious plan that has the potential to make the human species a multiplanetary species. And the result of all this effort is known today as Starship, the name given to the entire launch system that includes the main second stage spacecraft, which is called Starship, and the launch vehicle, which is called Super Heavy. Both vehicles are absurdly huge. And for the first time in the history of the rocket world, a spacecraft was entirely built from scratch, with the goal and the capability to take 100 or more people to Mars. For the first time ever, this uniquely designed spacecraft would have 4 control surfaces, 2 at the top and 2 at the bottom, instead of just 2, for an absurdly precise and never-before-seen control throughout the entire freefall and controlled descent phase through the atmosphere, which could be either Earth's or Mars. On August 6, 2021, Starship was first mounted atop the Super Heavy first stage prototype. Not only is it now the tallest rocket, but it's also nearing the status of being the largest, heaviest, and most powerful. After Saturn, yes, until then the largest and most powerful rocket ever made by humanity. But Starship has a single revolutionary and for some people even frightening feature: landing maneuver, which is mostly done with the spacecraft falling in a controlled way on its belly. To make things worse, the spacecraft returns to vertical orientation only 500 meters above the ground. But to understand why SpaceX chose this revolutionary and insane landing procedure, instead of opting to recreate the same type of landing used by the Falcon 9, and that has already been and continues to be exhaustively proven in terms of its reliability, we must understand how a vehicle arrives on another planet. When any vehicle arrives on another planet like Earth or Mars, among several other serious problems, it comes with one that is especially dangerous: the tremendous excess speed, which usually hovers around 20,000 kilometers per hour. And to start dealing with this problem, the team responsible for the spacecraft would choose to put it first into orbit around that planet to gradually reduce its speed, and then, in a more controlled way, carry out the procedure of entering the planet. But this can only be done if the vehicle or spacecraft has fuel specially reserved for this procedure, which generally speaking it never does. Besides being a more time-consuming procedure that greatly increases its complexity. That's why vehicles like the rovers end up entering the atmosphere at such high speeds that they end up overheating and catching fire. That's why they need to have very robust heat shields, and in the case of space shuttles, because they have wings, they needed not only heat shields, but they also needed to enter with a strong angle of attack and perform a series of left and right turns while descending through Earth's atmosphere. And this is where the incredible engineering behind the development of Starship comes into play. Starship also enters the atmosphere at an angle, just like the space shuttles, overheating and continuously slowing down as the atmosphere becomes increasingly dense. That's why it's covered by about 25,000 tiles that form its heat shield. But instead of gliding like the space shuttles did, Starship stays in a belly-down freefall, which is controlled and can be precisely adjusted by its 4 flaps. At around 500 meters altitude, its three Raptor engines ignite and vector to maximum, shifting the spacecraft from horizontal to vertical. At the same time, its rear flaps are retracted, making it even easier to perform the flip maneuver. Retracting the rear flaps while keeping the front flaps extended reduces drag at the back of the spacecraft, causing it to flip. With flaps retracted, less surface contacts the airflow and less drag is generated than on the top of the spacecraft, where the flaps are extended. But perhaps the biggest question is why SpaceX picked such an unusual and risky landing method, and why perform it so near the ground. To answer these questions, we need to understand a concept on which the entire Starship landing procedure is based. The so-called terminal velocity, defined as the maximum speed reached by an object in free fall through a fluid, such as air. In other words, any body in free fall will reach a point where it attains a maximum speed limit, and from that point on, the body will stop accelerating and will maintain an almost constant speed. Once this point is reached, the body has reached its terminal velocity. A person, for example, has a terminal velocity of about 200 kilometers per hour, while a raindrop has a terminal velocity of about 20 kilometers per hour. And the idea is to keep Starship at the lowest possible terminal velocity throughout the entire fall. So that, in this way, the spacecraft's terminal velocity is so low that it requires very little fuel to land it safely. And that's why the flip maneuver is done in the last moments, already very close to the ground. But let's take a closer look at this. During Starship's descent, there are two main forces acting on the spacecraft. The drag force acts upward, slowing the spacecraft down, and the force of gravity acts downward, accelerating the spacecraft. Starship will reach its terminal velocity at the moment when the upward drag force equals the downward force of gravity. In other words, both forces end up canceling each other out, and Starship stops accelerating and starts maintaining an almost constant speed. As the spacecraft continues falling, its terminal velocity actually decreases rather than increases, since the atmosphere gets denser and denser the closer it gets to the ground. But still, why fall on your stomach instead of vertically? If we compare the belly area of the Starship to its bottom area, it's clear that the belly has a larger cross-sectional area, generating much more drag than the cross-sectional area of the bottom of the ship. It's about 545 square meters of area compared to about 70 square meters of area on the bottom. In other words, that's 7 to 8 times more surface area, colliding with the air and generating much more drag, which consequently contributed to a much lower terminal velocity throughout the entire fall. That's why the rotation to a vertical orientation is only performed at the last moment, very close to the ground. But since Starship has flaps at the rear and at the front, things get much more interesting. By adjusting the flaps, Starship can maneuver like no other spacecraft. Retracting both right side flaps lets the spacecraft roll slightly to the right, in other words, turn to the right. Similarly, retracting both left flaps lets the spacecraft turn left. Basically, it's similar to the way airplanes turn, but without bending the wing and with a much lower and limited turn rate. Retracting both front flaps and keeping the rear ones extended, the nose dips down, so there's a slight increase in horizontal speed. In other words, the spacecraft is able to move forward, which can be useful when you want, for example, to escape from a danger zone for landing, or when the spacecraft is slightly behind its ideal landing spot. By retracting both rear flaps and keeping the front ones extended, you can bring the spacecraft back to its vertical orientation. And by positioning them symmetrically, you can make the spacecraft rotate. That is, perform a yaw movement, In other words, by adjusting the flaps, Starship can maneuver like never seen before and like no other spacecraft, while it falls in a controlled way toward the landing site. Since Starship descends and fires its engines while horizontal, modifications were needed for the engines to operate in both positions. With the addition of the so-called header tanks, which are auxiliary tanks completely filled with fuel, the main engines are fed through them during the final ignition, all the way to landing. That's because Starship basically uses up all its fuel during ascent, and the little fuel that's left stays at the bottom parts of the tanks, which, besides not being in the ideal location, is in low concentrations, which could cause the engines to fail or not function properly. And the ignition of the engines needs to be done at the exact moment. The procedure is popularly known as suicide burn, which is defined as the method of landing a rocket smoothly with well-calculated timing and the ignition of the engines at high power, started at the last possible second, so that it reaches a vertical speed of 0 precisely at the exact moment it touches the surface of the ground, and its engines are immediately shut off. And taking the Falcon 9 as an example, which is for sure the rocket that has performed the most suicide burns in all of history. If the engines are turned on too early, the rocket runs the risk of running out of fuel and ending up falling, damaging the engines and the landing legs. But it also risks slowing to 0 kilometers per hour while still airborne, which could cause it to rise again, a major problem. If the engines are turned on too late, the rocket runs the risk of not being able to slow down in time and ending up hitting the ground at high speed, thus destroying and probably the landing leg. That's why the suicide burn is used, in which the Falcon 9's computers calculate the exact time and moment to ignite the engines, so that it reaches an altitude of 0, almost at the same time it reaches a velocity of 0. And Starship follows exactly the same principle. And the main advantage of this whole procedure is that it uses much less fuel, or in other words, much less. Delta V is required to stop the entire system completely. And speaking of rocket engines, in general, there is an ideal zone for their proper functioning. In the case of the Falcon 9, this range varies from 40% power up to 100% power. Anything below 40% and the engine runs a serious risk of flame out or simply shutting down. So the ideal setting is around 70% power. This allows the computers to increase the power if ignition happened later, or reduce the power if ignition happened earlier. Computers do this fully autonomously, constantly calculating descent speed and acceleration, and how much power is needed for the rocket to reach an altitude of 0, almost at the same time it reaches a speed of 0. And a little curiosity about the proposed final moments of the Falcon 9. With just one Merlin engine at minimum power, it generates enough thrust to make the rocket hover in the air. That's how powerful these engines are, and why the suicide bird is so important. And just for comparison, during the fall, the terminal velocity of the Falcon 9 is around 310 meters per second, or 1,116 kilometers per hour versus 150 to 100 meters per second, 540 to 360 kilometers per hour for the Starship. That's because the Falcon 9 falls vertically, so less surface area hits the air and less drag is produced. Returning to Starship, as with all space exploration, the risks are huge and ever present. Everything has to be and work absolutely perfectly for the mission to be a success and for there to be no loss of life. That concept truly defines space exploration, as it's full of risks. Maintaining a spacecraft in free fall, belly down, until positioning it just meters above the ground on any planet. It's an extremely viable task in terms of cost reduction and from an engineering point of view. But it's also very dangerous due to human factors. Although we have already sent and successfully landed several rovers and probes on Mars, making it almost routine, contributing tremendously to the expansion of our knowledge about other planets. The manned journey to Mars is much more challenging. A trip from Earth to Mars takes about 7 months, and, as has been exhaustively studied and proven on the International Space Station, the human body undergoes constant and significant loss of muscle and bone mass, as well as muscle atrophy, at a much faster rate compared to those on Earth, precisely because of the absence of gravity. That's why astronauts are required to exercise for a little over 2 hours a day to fight this loss. This means that inside the Starship, there must necessarily be multiple machines so that astronauts can exercise regularly. In addition to confinement, health, and crew communication and relationships, ensuring enough food and water is also critical, since it's 7 months to get there, and a few days or weeks there, and another 7 months to come back. You need enough food and water for 2 years of travel. And the water won't just be for the crew's consumption, but also for hygiene, equipment cooling, and even for the crew's breathing, although other methods can also be used for oxygen production. Only time will tell how these problems will be solved. Meanwhile, Starship continues to be exhaustively tested and improved with each passing day. And maybe one day this landing will be as common as the landing of the Falcon 9's first stage, but not here on Earth, but on the sea.